Hello, I am Mr. Clark, and in this video we're going to have a look at how to construct a Born-Haber cycle. So we're going to have a look at the first question on your Born-Haber cycle worksheet, which is constructing a Born-Haber cycle for cesium iodide. Now these are like a really glorified Hess's law cycle. So if you follow exactly the same principle as a Hess's law cycle, you'll be fine. It's the idea that the total energy change is the same regardless of the route taken. And Born-Haber cycles are typically talking about the energy required to make an ionic compound. So in this case we're going to look at the energy required to make cesium iodide. Now that is usually trying to find out the lattice enthalpy, the delta H lat, the lattice enthalpy for cesium iodide, where you form cesium iodide from cesium ions and iodide ions in their gaseous state. And we can get this data here by working out all of the different steps involved in turning the compound into a gas and ionizing each species. So let's have a look at how we construct this. So starting off with cesium iodide solid ionic compound on the bottom, and we're going to look at the enthalpy change of formation of that. So the enthalpy change of formation is with cesium in its standard solid state and iodine in its standard solid state, but iodine is a diatomic molecule, so we're going to have half of an I2 just because we only need one of them. The delta H of formation is when 1 mole of a compound is formed from its constituent elements in their standard states, so this arrow goes down, and that is the delta HF of cesium iodide. So what stages do we have to go through? So now we've got these two species here. The first thing we need to do is it's called atomization. We need to get those into their gaseous state. So let's do it one by one. Let's do cesium as a gas, and then plus half I2 solid, and then let's do cesium still now in a gas, and let's do plus I gas. Now we've turned it into a gas. It's not half an I2 anymore. It's just an iodine, just one iodine atom. So let's just fill in some labels so that you can see. So this energy change here is the delta H of atomization of cesium. This is the delta H of atomization of iodine, and these changes, the arrows point upwards. So you're going from there to there, from there to there. So and then what we need to do is we need to get these species as ions. So let's look at the first one, would be the delta H of ionization of cesium. Let's say I1, the first ionization of cesium. So at the top now we're going to have cesium plus gas plus I gas. The next one is we need to make an iodide, so we need to add an electron to the iodine atom. So what we can do here is it's called an electron affinity, so the affinity of an electron, so adding one electron. So the delta HEA of iodine is that, and these changes, the arrow points up, and then as part of the cycle we're adding an electron, this one goes down. So now you can see we've constructed a cycle with lots of complicated terminology on it, and we need to work out a value of an unknown. So let's plug in from the data you're given. You're given some data, let's just plug in the values that you're given. So the delta H formation here is minus 337. The atomization of cesium is plus 78. The atomization of iodine is plus 107. The ionization of cesium is plus 380. And the electron affinity is minus 295. So we've just got some values annotated on that table. Just bring it into focus a bit more. There you go. Right, so here's how I do it. Now, there's other methods available. I'm sure some of you will just try and punch it straight into your calculator, but here's how I do it. I'm just going to label them arbitrarily. Let's say delta H1, delta H2, delta H3, delta H4, delta H5 and delta H6. And then we can construct an equation which follows the arrows around. So you can see that as a cycle, this arrow goes one way, but for the rest of the cycle, the arrows go the other way. So we can do just writing a simple equation, delta H1 equals delta H2 plus delta H3 plus delta H4 plus delta H5 plus delta H6. Alright, that's just a simple representation of that cycle. So what I'm going to do is I'm just going to add in numbers, just taken straight from the table. So we have minus 337, delta H2 is plus 78. Now I'm just going to say to you, just write things out nice and normally. So we're adding here, delta H3 is 107, delta H4 is plus 380, and delta H5 is minus 295. So if we're going to add minus 295, I like to do it like that, where you add minus 295 over here, just so we're not mixing any arrows straight away, mixing any signs straight away, and then that's all plus delta H6. So just crunch through those on your calculator and you should end up with minus 337 equals delta H6 plus 270, and all of a sudden the algebra becomes quite a lot more simple. So plus 270, and we take 270 away from this side and 270 away from that side, and you end up with your lattice enthalpy being minus 607. Okay, so it's minus 607 kilojoules per mole. You can write a final answer down here, and it's really all about inborn Haber cycles, just keeping your wits about you and not jumping too many steps at once. So remember, it's formation and then turn them both to a gas, atomization, ionization of the cation, electron affinity for the anion, and then that's the lattice enthalpy there. Alright, once you've done a few of them, you'll get more familiar, and hopefully this video has made sense to you and helped you out a little bit. Thanks, bye bye.